The periodic table of the elements is one of the most iconic and recognizable scientific tools, known worldwide for its ability to organize the known elements of the universe. It's a tabular display of all known elements, organized by their atomic number, electron configuration, and chemical properties. This organization allows scientists to predict the behavior of the elements, discover new elements, and understand the patterns of chemical reactions. What's absolutely amazing about the periodic table is it consists of just over 100 individual elements, and every single substance you've ever been exposed to in your entire life is just made up of different combinations of these elements. Whether you're, eating a banana, writing with a pencil, burning a campfire, everything you've ever touched is simply different combinations of these roughly 100 different chemical elements. The periodic table is organized into rows, which we call periods, and columns, which we call groups. The periods, or rows, represent the number of electron shells in a chemical element, and we'll be talking about electron shells and electron configurations here shortly, while the columns, also called groups, denote the number of valence electrons. Basically, that's the number of electrons in the outermost area of the electron cloud around an atom. When we group them like this, then the elements in the same group or column have similar chemical and physical properties due to their shared valence electron configuration. For example, the noble gases, which have a full outer shell, are all located in the far right column of the table, and they're unreactive. These are gases like helium and neon and so on. They're completely unreactive. One of the most important uses of the periodic table is when we organize them this way, we look in the column and they have similar chemical properties. So you can almost predict how an element is going to react just by knowing what column it is in the periodic table. We'll be talking about this very, very shortly in more detail. The periodic table is used in a wide variety of scientific fields, including chemistry, physics, and material science. It provides a framework for understanding chemical reactions, predicting the properties of elements and compounds, and designing new materials with desired properties. The periodic table is also used in education, where it's a common tool in chemistry classrooms around the world. Now, to me, one of the most amazing things about the periodic table is that if you pick two random elements and you understand their properties, they may form a product that's completely different than the two elements that make them up. For instance, hydrogen is a colorless gas. You have to get hydrogen very, very, very cold in order to turn it into a liquid hydrogen, right? But it's colorless. And also you can look at oxygen. Oxygen is a gas that's more massive than hydrogen, but again, very, very cold temperatures are needed to liquefy oxygen, right? So hydrogen, colorless gas. Oxygen, colorless gas. If we put them together and burn them, that's what we use in rocket fuel. And what is the product of this? Well, H2O. Water is the product of this, and water has completely different properties than hydrogen and oxygen. Water is a liquid at room temperature. We drink it. We use it to dissolve substances. So by combining the different elements, you get chemicals that are totally different in properties from their parent elements. Now let's roll up our sleeves and dive into the periodic table in a little more detail. So in the beginning, when you look at a periodic table, it just looks like a chart with squares on it. But then at the end of this lesson, the goal is going to be to take that apart and understand why it's constructed the way it is. What value does it bring? Why do we care about it? How do we use it? And a few other things along the way as well. So without any further ado, let's just talk about this periodic table. So this is what we call the periodic table of the elements. Whatever textbook you're using, or if you're on the internet or whatever, you can find many different flavors and varieties of the periodic table. They're going to look different than the one that I have here. So if you have one printed out or in a textbook or whatever, just pull out the one that you have and follow along. They all have generally the same structure, but of course they'll look a little bit different. All right. Now, the big picture of the periodic table is that it contains all of the different kinds of elements, which are different kinds of atoms, that are what we use as the building blocks to create and to basically form everything you know around you. Everything you've ever touched, everything you've ever eaten, everything you've ever, had pleasure or pain from, or any stimulus that comes into contact with your skin, a rash, any kind of food, any kind of, playground equipment, cars, whatever. your whole entire body is made of these elements and configured in different ways, right? So what we're going to find as we study and examine this is that we're going to learn about the entire table, but we're also going to recognize that we're going to use parts of this table a little more heavily than others. I'll tell you right now that we're going to learn the structure of this whole thing, but really we use the left-hand side of the table and we use the right-hand side of the table more than anything else. Now, does it mean we never use the elements in the middle? Of course not. We use them, but we don't use them as much. In a chemistry class, which we call Inorganic Chemistry 1 or General Chemistry, we use these elements here and mostly these elements here, and of course we use these over here as well, some as well. Now later, after you take Chemistry 1 and Chemistry 2, you take a class called Organic Chemistry. We're going to talk a lot more about what that means a little bit later, but basically organic chemistry is chemistry of compounds that contain carbon. All right. Carbon is a very special element because of the way it bonds to other atoms. It allows long molecules like DNA to exist. Carbon is right here on the periodic table, and when we say organic chemistry talks about carbon, really it's carbon along with a few other very important elements. So in organic chemistry you have carbon, nitrogen, oxygen, hydrogen, and then a few others sprinkled around. And it turns out there's just a handful of elements gives rise to life and the complexity of life, DNA and very complex molecules. Now we have to crawl before we walk. So how is this table arranged and why is it important? All right, the first thing you need to know is that this periodic table is arranged in order of increasing atomic number. Remember, you can see right here in the legend, every square on this table has a chemical symbol or an elemental symbol. In this case, Hg is the symbol for mercury, and the letters don't really match because a lot of the time the symbol for the element comes from the Latin word that was used when it was first discovered. So Hg, is because of its a Latin root. But most of the time it's like O for oxygen, and N for nitrogen, and C for carbon, and B for boron, and P for phosphorus, and most of the time it lines up, but sometimes it doesn't, okay? And then on every one of these squares, we have the name of the element, we have the atomic number. Remember, we've already learned the atomic number is the number of protons in the nucleus, all right? And then, of course, we have the average atomic mass down here, which we've already also have learned about in great detail. The atomic mass, just as a reminder to you, is the average, the weighted average of all the different isotopes of an atom or an element. So if you don't know what those words mean, then go back to my previous lessons because we discussed it in great detail. Basically, in the nucleus, we have protons and we have neutrons. So what makes an element different from its neighbor is the number of protons in the nucleus, right? So this is hydrogen has 1 proton in its nucleus, and helium has 2 protons in its nucleus. Lithium has 3 protons in its nucleus, and beryllium has 4 protons in its nucleus. But in the nucleus, in addition to the protons, we also have neutrons. And that's where things get a little fuzzy because the element is defined by the number of protons you have, but the nucleus can have a varying number of neutrons, which makes it either heavier or lighter, and those we call isotopes. So we may have different isotopes of oxygen, we may have different isotopes of carbon, but they're all chemically the same element. It's just they may have more or less neutrons in the nucleus, and that is what gives rise to different weights of those isotopes. And they exist in different percentages in nature. There's always a most stable common isotope. So this average atomic mass is taking the average of all the different flavors of the isotope. So for instance, nitrogen, or let's look at carbon, has an average atomic mass of 12.01 atomic mass units. This is the weighted average of all the different flavors, which we call isotopes of carbon that exist in nature. We have a very common, stable isotope of carbon that we have all around us, and then we have some others that are not so common. So when we mathematically average all of the common ones with the uncommon ones, which all have different masses, we get an average mass. And that average mass is what is printed everywhere on this table. So every number, for instance, zinc here, has a mass of 65.39 atomic mass units. But this number is the weighted average of the different isotopes that exist in nature for that element. And every element is like this, okay? Because every element, with very few exceptions, I believe, we always have different amounts of isotopes, which can be different numbers of neutrons in the nucleus. So the big thing to understand is this thing is arranged an increasing atomic number. If you have an element with only one proton, we call it hydrogen. If you add a proton to it, then you get something called helium. Now remember, every one of these elements are neutral atoms. So you have to have, for a neutral atom, the same number of electrons on the outside, orbiting around, or in the electron cloud around the nucleus. You have the same number of electrons as you have protons in the nucleus in order for you to have a neutral atom. So without writing it all out, you know that nitrogen, for instance, has 7 protons in the nucleus, and it must have 7 electrons surrounding the nucleus. You know that chlorine has 17 protons in its nucleus, and it must therefore have 17 electrons around its nucleus. And the same thing, you have niobium, for instance. Niobium has 41 protons in the nucleus, and it must therefore have 41 electrons surrounding the nucleus to have an electrically neutral atom. And then each of these also have varying numbers of neutrons, and so all of that goes into the calculation of the mass. So the thing to remember, though, is as you add protons to the element, it becomes a new element. So if I start with hydrogen, if I could magically add a proton in the nucleus, then it would make helium. In fact, when you fuse hydrogen together in a nuclear reactor, then you can make some helium. If you take helium and you can add a single proton to it, it becomes a new element called lithium. If you start with lithium and add a proton to it, then it becomes beryllium, and you see how this goes. So it's the periodic table of the elements, but it's arranged in order of increasing atomic number. Now, let's talk about the elephant in the room. Why is it called the periodic table of the elements? Why is it periodic, is what I'm trying to say. So forget that we have this table now. Forget that we know what it is. Forget that we understand anything about chemistry. You live a couple hundred years ago, and you're a scientist, and you just have a lot of things in nature that you're studying. And you believe you boil them down to these fundamental things that are all different from each other, and you call them elements or call them atoms, okay? What you basically figure out is that what happens is when you make a list of all of the things that you've collected from your lab, and you arrange them in order of atomic number, what you basically have is you have some periodic behavior in the atoms. So what you have is you have an element over here, and then you get to an element that you call helium, right? And then you have some other elements here, and then you end up with another element that you call neon. And then you have some other elements here, and then you end up with another element called argon. And then you have some other elements, and then you end up with another element called krypton. Like this. And I can keep going. I'll just do one more here. And then you have another one here called xenon. You see what I've done is I've basically written down these elements in the right-hand column here. You'll understand why it's in the right-hand column in just a second. But let's say you don't know anything about chemistry. What you notice is that every so often you have a non-reactive gas. Non-reactive gas. And the interesting thing is this gas is non-reactive, this one's non-reactive, this one's non-reactive, and also this one's non-reactive. And what I mean by non-reactive is they don't participate really in any chemical reactions, right? And that is true. I'm going to boil it down and show you how this occurs in a minute, but basically everything in the right-hand column, we call these the noble gases. They're noble, right? They're kind of like keep to themselves. They don't participate in chemistry. They don't make anything in a chemical reaction. You can try to put whatever you want next to argon, and with very few exceptions, it's not going to bond with anything. Like, water, right, is H2O, so 2 hydrogens and 1 oxygen. So they bond together and they make a molecule, and you can drink it and you can cook with it and all of this. But you really cannot make these things react with anything, and that's a curious thing. But then people realize, even more interesting than that, is the fact that whenever you look at these special gases, first of all, they're all gases that are non-reactive, okay? And then what you really look at is that the element that comes right after, again, when you're increasing atomic number, the element that comes right after each one of these is a very, very reactive soft metal. So I'll go down here, soft, reactive metal. Right? Every time. So right after neon is a soft reactive metal. And what I mean by reactive is it reacts with lots of things. It reacts with oxygen, maybe it reacts with water, and you can just tell that chemistry is happening. Chemical reactions happen. And it seems to happen like they have these perfect gases that don't do anything, and then right next door you have a very, very reactive metal, okay? Increasing atomic number. And then also on the previous side, like over on this side over here, I guess I'll use this color, there's an interesting little thing right here, is that you have in general a gas over here that is a reactive gas, all right before. So you can just see that there is some periodic nature to what's going on, because when you take all the elements that you discover and you put them in order, forget about the table, you just write them in a straight line from beginning to end. There's 100 and some odd elements here. You put them from beginning to end. What you're going to notice is that there's some kind of regular repeating patterns here. There are these special ones, these special elements, which we now call the noble gases, which don't do any chemistry at all. No matter how much you want it to happen, it won't happen. But then on either side of the noble gases, they're extremely reactive elements. And it always happens that the element just after the gas is a metal that's soft and very, very reactive. And just before the gas is another gas, which is also quite reactive. All right, so this is what happens when you put them in a line. So people start playing with this table and trying to figure out what does it mean and why do they behave this way. And eventually, after a lot of different scientists, they come up with the formulation of the periodic table. So now knowing the periodic nature of what it is, let's look over here. Well, the way we've arranged this is increasing atomic number, but of course the table looks weird. There's a big gap right here. This is not lined. There's a big gap here. There's a gap right here. It doesn't look like a nice square table. And I'm going to tell you right now that the reason it's laid out the way it is, it all has to do with how the electrons around all of these atoms are actually set up, how they're actually orbiting there. We're going to get to that a lot later. So we can't do too many things at once. I cannot tell you the electron structure around aluminum right now, because it's going to be too much at once. But you're just going to have to trust me that the way that this table is laid out, the way that it looks, it comes directly from how the electrons fill into the orbitals that surround all of the atoms. We're going to get into that in a great detail a lot later. But if you notice, here's helium. It's one of these noble gases. And just after that is lithium, which actually is a very highly reactive soft metal. And then you keep going over here and you get to neon. And right after neon, remember, it should be a soft reactive metal, which is sodium. It's a soft reactive metal. And then when you get to argon, right after that one, because this is non-reactive, you get to potassium, another very soft reactive metal. And after krypton, you get to rubidium and the same kind of behavior. And then also, we said, remember, after the noble gas comes a soft reactive metal, and before is in general a very reactive gas. So here in front of neon, we have fluorine, very reactive gas. In front of argon, we have chlorine, very reactive gas. In front of krypton, now this is not a gas, bromine's not a gas. So there's some exceptions here. They're not always gases that are on the right before the noble gases, but it's often the case. So it's enough to convince you that there's some periodic nature. Now let me give you a clue, because we can't study it in detail in this introductory lesson. The reason why there's periodic structure to the atoms in nature, the reason why we see these patterns, is because the way the electrons fill in all of the orbits around the nucleus, it follows a regular repeating pattern. That's the reason why. Now, of course, in the beginning, when they made the periodic table, they didn't know about electrons at all. They hadn't even been discovered yet. That's what's amazing. They put this table together without even knowing what the atom was, okay? They also didn't know about protons and neutrons either. But now we know that the reason why all of these noble gases are very unreactive is because they have the very same electron configuration in their outermost shells, which are all very similar. Now, what do I mean by very similar? I have to save that for another lesson because it goes into some details. But every one of these has a very similar outermost shell. Okay, outermost shell. We're going to talk about what shells are, but basically the electrons, you can't just pile them in. They have to occupy certain states around the atom, and they're organized into shells and other things. And so the outermost electrons of all of those are extremely stable. And that is why they don't like to react with anything, because all chemistry, chemical reactions, basically centers around how do the electrons move around.
When you have a reaction, you have an electron sharing or an electron transfer taking place, and then the atoms can rearrange themselves, and then you have something new, the product of the reaction. But in here, because the electrons are all extremely stable around all those atoms, they don't want to react with anything because the electrons don't want to move. And that is why the noble gases don't react. All right, so we said that we had the noble gases in the right-hand part of the table. We said that just after the noble gases, we had a very reactive column here of very reactive metals. Then we talked about in every one of these squares, we have an atomic symbol, an atomic number, which is number of protons, and the atomic mass. And depending on the table that you have, you might have other information in here. This table also has something called the electronegativity. We're going to talk about what it means later. Don't worry about it now. It has to do with how the atom attracts electrons, okay? But you could have all kinds of things in different periodic tables. You might put the melting point of the substance or the boiling point of the substance, or what kind of crystal structure the substance has. Or you might put, like this one has electronegativity. You could have all kinds of things in periodic tables. But the most important things, the ones you'll see everywhere, is you'll see the symbol, you'll see the atomic number, and you'll see the atomic mass. Anything else is just, you may or may not see that. That's the core of the periodic table. Now, before we go any further, I've told you that there's a periodic nature, and I've told you the reason why there's a periodic nature in some of the properties. It's because of how the electrons are situated around these atoms. Now, I need to give you more definitions. I'm not going to write these definitions down because it'll be a waste of my time and your time, but I will tell you, and I encourage you to watch it several times to make sure they sink in. They're not hard, but we have to talk about them. So this periodic table consists of rows over here and columns, which are here, okay? But we don't call them rows and columns. We actually call the rows, we call them periods. That's why, one reason why it says periodic table. So this is a period, period number 1. This is a period, period number 2. And this left side, you can kind of think of it being connected to the right side, sort of. You draw your finger all the way across. This is period number 3. Period 4, this is period 5, this is period 6, and this one down here is period number 7. So the periods go across. Periodic, period, okay? Now, the columns, we don't call them columns, we call them groups. So this is a group. See, it's labeled at the top, group number 1. This is a group. It's called group number 2. This is group 3, group 4, and you can see that you have a nice little vertical nature to it. We have the groups, and then we have group number 13, group number 14, group number 15, 16, 17, and 18. All right? Now, the interesting thing about the groups is that the groups, one of the main reasons why we use the periodic table is because the elements that are in the same group, which is the same column, remember column means group, elements that are in the same column have similar properties. I'm going to say that again. Elements that are in the same group have similar properties. I'm going to say that a third time. Elements in the same group have similar properties. A fourth time. Elements in the same group, up and down, have the same or similar properties. That's critically important to you. Critically important to you. In fact, it's one of the most useful things on this table because you can see right away that these must have similar properties. And what is that property? They're non-reactive gases, okay? That's a big one. These have a similar property in group 1 right here. They are extremely reactive metals, but let me come back to hydrogen because hydrogen is a little bit of a weirdo. Obviously, it's not a metal, but everything else is an extremely reactive metal. These are also extremely reactive metals, but not quite as reactive as these, right? Now, when you go to this side of the table, these have similar properties. They're mostly gases. There's some solids here as well, but they're very similar properties as you go. You can see it right here as well, because in this column, you have copper, you have silver, and you have gold. Copper, silver, gold are basically what we have used over the years to make all of our currency. So sometimes we call it the currency group, right? And the reason why we use these particular elements, why don't we use, iron? Well, iron rust, or how about cobalt, or how about niobium or titanium? I mean, some of them could be useful. There's also different abundances in nature. So these elements are they don't all exist in the same abundance on Earth, okay? But copper, gold, and silver are in reasonably high abundance on Earth, and they're relatively non-reactive as far as metals go. I mean, silver does tarnish a little bit. It turns like a little grayish after a while. It does tarnish, but gold and copper, I mean, there's a little bit of copper reacts a little bit too, but in general, compared to other metals, they don't react as much, and they're very strong and they last a long time, and we can stamp them. We can also pull them. That lets us make our money out of them, right? And that's why we basically use those. So what I'd like to do is tell you at this point, other than the idea of periods, which are rows, and groups, which are columns, and I want you to know that the elements in the different groups have similar properties, one of the absolute most important things that you have to understand here is that the left-hand side of the table, the entire left-hand side of the table is in general metals. In general, metals on the left-hand side. On the right-hand side of the table is in general non-metals over here. And in the middle, what we have here, down here, set below, we call these the transition metals here. And we're going to learn a lot more about why they're called these different things a little bit later. This is an overview lesson. But if you just take a look, notice that there's this stair-step line right here. It kind of divides the table from a left-hand side to a right-hand side. Everything to the right, you might guess that it's a non-metal. I mean, chlorine, oxygen, nitrogen, carbon. Carbon's definitely not a metal. And then you have all these gases like neon and helium and things like this. And then over on the left-hand side are the things that you might think of as metals. You have your copper, your zinc, your nickel, your titanium. Some of these others you may not know about as much. You know, you have rhenium and gold and mercury and platinum. And then over here, these are metals as well, but we don't, see them much every day because they're so reactive. They're usually already combined with oxygen. Like here you have sodium and lithium. Now you actually eat sodium every day because sodium chloride, which is an atom of sodium combined with an atom of chlorine, makes something new called sodium chloride, and that is table salt. So these things you have experience with, you just may not know that table salt is sodium chloride, okay? So anyway, the left-hand side of the table are the things that you typically consider to be metals, and the right-hand side of the table are things that you typically consider to be non-metals. And right around this stair-step line is the border between the two, and so the elements that are right on the border, we typically call those metalloids. We call them metalloids, all right? Germanium and silicon are probably the most important ones, but boron and some of these other ones on the border here. So silicon is probably the one you've heard of the most. Silicon is extremely important for making all of our computer chips. Imagine the world without computer chips. And when I mean computer chips, I mean any kind of chip. Any kind of transistor, which is what we make our radios out of. So you have no radios, no phones, no televisions, no internet, no satellites, no spaceships, no screens of any kind of screen without any silicon, right? So silicon is really important, and silicon is right on the border of the metals and the non-metals because silicon has properties of being a metal and also properties of being a non-metal. You know what that lets us do? That lets us build things out of silicon that can behave as an on-off switch. So when we want silicon to conduct electricity, we can make it do that, but when we want it to not conduct electricity, we can make it do that too. So it can behave as a switch. And guess what? A transistor is what is basically a switch. That's what a transistor is. It's a tiny microscopic switch made out of silicon. And when we put a bunch of transistors on a chip, then you can have a computer. And so without transistors, you can't make computers. Without computers, you can't do anything in the modern world. And none of it's possible without silicon. So this is an extremely important element. Right above silicon is, of course, carbon. And carbon is the building block of life on Earth. I mean, who knows if there's life elsewhere that not based on carbon, but on Earth, anyway, as far as we can tell, it requires carbon to exist. So I want to make sure I get through everything because I have a lot of stuff to say. We talked about the periods, we talked about the groups, we talked about the properties of the elements and the groups being the same. Now, on the left-hand side of the table, we have the metals. On the right-hand side of the table, we have the non-metals. In the middle, we have the transition metals. And if you notice down below the periodic table, we also have this extra row right here, which actually this extra row consists, these are pretty high atomic number atoms here. And we have, these actually fit inside of this little region. You see 57 to 70 and these numbers here. This entire row right here actually fits inside and pushes the table to the right. I'm going to show you a picture of that in a second, but all of these elements kind of live inside of here. So just hold tight and I'm going to show you what that looks like. What I want to do now is I want to tell you one of the absolute most important things that you need to know about the periodic table. I don't really have to mention it now, but we're going to use it so much I want to introduce it to you. If you don't remember it at the end of this, fine, no big deal. What you really have with this periodic table is you have these non-reactive gases, which we call noble gases. And they're non-reactive because their electrons are stable and they don't like to be shared or given away, and so they don't react with anything. That's what we have there. It turns out that the other elements nearby the noble gases are always trying to get to an electron configuration that is as similar to a noble gas as it can get. I'm going to say that again. All the elements on this periodic table are always trying to get their electrons to look like noble gas electrons. What I mean by look like it is we want them to have the same number of electrons in the same orbital shells that we're going to talk about later, right? So what we have here is, notice that neon, for instance, neon has 10 protons, and so it must have 10 electrons. So fluorine is right next door. It has 9 protons, and so it must have 9 electrons. But fluorine is always trying to be as close as possible to the nearest noble gas it can be, which is right here next door at neon. So if it has 9 electrons, all it needs is 1 additional electron to have the same number and orientation of electrons as the noble gas. Everybody's trying to be like a noble gas. And so what does fluorine want to do? It wants to gain a single electron. It wants to gain an electron. Chlorine is always trying to be as close as possible as it can to argon in terms of its electron count and the structure of its electron. So it's always trying to gain an electron. And the same thing with these other ones here. But see, oxygen is 2 spots away from neon. And so the closest noble gas is neon. Of course, you could go this direction and say that there's another gas called helium, but that's too far away. It wants to be nearest to the closest one. So it wants to gain 2 electrons because it currently has 8 and it wants to have 10. And if it can gain 2 electrons, it'll have the same outer electron configuration as its nearest noble gas. So the column that it's in is telling you how many electrons these things want to gain when they participate in chemistry. That's what drives the chemistry. They want to gain electrons because they want to be closest as they can be to a noble gas. And that's what drives the chemistry. Because when elements gain and lose electrons, that's what makes chemistry happen. And I'm telling you now how you can figure out on your own how many electrons it wants to gain. In this case, oxygen wants to gain 2, fluorine wants to gain 1, and so on. Carbon can gain up to 4 electrons, and that has to do with the importance of carbon, for instance. Okay, now over here, notice to the left of neon, if we unfold the table and just write them in a straight line, one spot to the left is, well, let me go look at sodium, I guess, atomic number 11. So what noble gas does this thing want to be next to? Well, it can go all the way down here, and you could say it might be attempt to be like argon, but actually the nearest noble gas to this one is the noble gas just on the previous row, because this has 10 protons and 10 electrons, but sodium has 11 protons and 11 electrons. So how could sodium, if given the choice, be as close as possible to the nearest noble gas? The much easier way, sodium would have a hard time gaining all these electrons to be like argon. That would be very difficult, okay? But what it can do is it can just give away an electron. What if it just gives one of its electrons away? So now it only has 10. And then it would look just like neon. You have the same thing with potassium. Potassium wants to be like its nearest noble gas. It's going to give away an electron, thereby having 18 electrons. And look at this, argon has 18 electrons. So if it gives an electron up, it becomes like the nearest noble gas. If this one gives up an electron, it becomes like its nearest noble gas, and so on. And we can do the same thing in the column next door. What would magnesium want to do? Right? Of course, it could try to gain electrons and go here, but that's too far away. It would rather just give up 2 electrons and become like neon. So everything in this column is going to give up 2 electrons and become a positive ion, because remember, if you're neutral and you give electrons away, then your nucleus has an extra positive charge. You're going to have a positive 2 charge. So when you give away electrons, you're going to have a positive charge remaining left over on the atom. We call that an ion. We're going to talk about that in a little bit. But this column wants to give away 2 electrons. This column wants to give away 1 electron. This column wants to gain an electron, becoming a -1 ion. This column wants to gain 2 electrons, becoming a -2 ion. So once again, this column wants to gain 1 electron. This column wants to gain 2 electrons. This column wants to lose 1 electron. This column wants to lose 2 electrons. And this column doesn't want to do anything. It doesn't want to gain or lose anything. Now, I want to take a second and tell you about a pet peeve of mine that when you read different books or you just talk to people, I don't like using the words, this element likes to do this. This element likes to do that. I know I said that a bunch here, but I really don't like using it because it leads you to believe that these elements have a personality and they just have preferences. It's not that they have preferences. It's not that they want to be like a noble gas. It all comes back to what I told you in lesson number 1. Everything in chemistry comes down to the electric force. The force of electric charges is millions and millions of times stronger than gravity. And I showed that to you in a previous lesson, right? Millions and millions of times stronger than gravity. We think gravity is really strong, but actually the electric forces are way stronger. So why does this thing want to gain an electron? Quote unquote, want to gain an electron. It's not because he wants to, because he has a preference. It's because the electric forces are so strong on this thing that they allow fluorine to suck an electron in from almost anything it reacts with. Right? Why is it allowed to do that? We're going to have to talk about that later when we get to showing you what the structure of the electrons look like and the electric forces that happen. I can't do it all in one lesson. But the reason fluorine and chlorine and bromine and these things want to gain an electron so readily is because the electric forces are so strong they can suck in and attract and rip out a negative electron from something else. And why does sodium and lithium and these other things, why do these elements here want to lose an electron? Well, it's because the outermost electron on those atoms is not held very, very strongly from the electric force, so the hogs like fluorine and chlorine are able to rip it away. So you see on the left side of the table, you have outermost electrons that are not really tightly held on by the electric force. We're going to talk about why later. But these atoms have outer electrons that are not held very tightly by the electric force. And these elements over here, they want to attract, and they do attract electrons so readily because their situation is opposite, and they are able to attract electrons with overwhelming force. So what happens is it just sucks the electron from this side, and it goes into this side, and that's why sodium, chlorine react together. Because chlorine really wants to grab an electron and has a very strong electric force to do so, but sodium has an outer electron that's not very tightly bound, so what happens is chlorine just sucks sodium electron over there and it satisfies both parties. And then they bond together and they become table salt. What I'm telling you here about predicting if you're going to gain an electron or lose an electron is one of the most important things the periodic table is for. In fact, I would go as far as to say it's probably the most used thing on the table, except for the atomic mass. We use that a lot too. Mostly when you're looking at the table, you're trying to figure out how many electrons something's trying to gain or lose, because that's going to help you predict what's going to happen in the chemistry. And by knowing the column it's in, which we call groups, by the way, what group it's in, you can predict what's going to happen because you'll know how many electrons it's going to gain or lose. So in summary, on the right-hand side of the table, these elements in general are trying to gain electrons. They are called nonmetals, right? And they gain electrons and become more negative, and they become and look like the outer electron configurations of the noble gas. These elements over here, they try to lose electrons, and they try to lose as much electrons to also be like its nearest noble gas. So because half of the table is trying to gain electrons and the other half of the table is trying to lose electrons, they can party all day long because one element is readily able to give up an electron, the other element is readily able to take an electron, and then they're going to party because they are a match made in heaven, okay? So we're going to talk a lot more about that, but that is the basic idea. The elements in the center, they're also metals. They generally do like to give up electrons as well, just like these, but they're not quite as reactive, and the rules associated with these middle elements are not as cookie cutter, okay? The elements on the edges of the table, we can predict with great certainty what's going to happen. The ones in the middle of the table, they can do different things depending on what's happening, so it's not quite as, like I said, cookie cutter. So let me go down and make sure I have everything. So periodic tables arranged by atomic number, properties emerge. We have noble gases, non-reactive on the right. We have right next to it on either side, we have very reactive elements. We have atomic number, atomic mass, periods, groups, losing and gaining electrons. And then the next thing I wanted to show you was the bottom of this table has these two rows, which are also always down below. I never really understood when I first learned chemistry why it was down below like this. Let me show you. These elements really fit inside of these single boxes, and they push the table out. But because they push the table wider, you can't print it so easily on a sheet of paper. So let me show you what it would look like if you did that. This is what the periodic table actually looks like with those two rows inserted, or the two periods. These two periods inserted into place. Notice what happened is we stuck them in there, and then basically the whole table got pushed to the right. And it's a little more difficult to read it because it's so wide right now. but this is S, C, and Y, yttrium, right? So here is scandium and yttrium. So what happens is these two rows go in here and they push you basically cut it right here and it pushes the table to the right, and every one of these elements exist in here. And you can see that that is what happens here. So it goes in here. So when you look at the table like this, you know, at first you kind of get used to the periodic table, and then when you see it like this, a lot of times you're like, why does it do that? Why is it that way? Why does it have just like these top two elements by themselves, and then we have some stuff here, and there's a big gap over here, and then there's even a bigger gap right here? Why are the gaps everywhere? All I can say is everything will be revealed in time, but it has to do with the electrons. Everything has to do with electrons in chemistry. It basically boils down to how the electrons fill up in the shells surrounding the atom. And that dictates how many, that dictates all the spacing here. I'm not going to say any more than that because we have to talk in more detail, but that is the reason. It's because when the electrons are filled up, they fill up in a certain way, and that dictates the structure of the table, which we will get to in a lot more details later. A couple more things I want to mention before we finish this lesson out and do our problem. And that is that I kind of glossed over this in the beginning, but I basically told you we have periods, period 1, period 2, period 3, and then I said we have groups. This is group 1, group 2, 3, 4, 5, all the way to group number 18. Now, that is the modern labeling, group 1 through group 18. So that is the modern labeling, which is dictated by an organization called IUPAC. You're probably going to see that or hear about that in your class. IUPAC stands for International Union of Pure and Applied Chemistry. So it's a governing body who determines how things are named, basically, and how things are labeled. And so it leads to very little, it's very clear to say this is group 1, and this is group 12, and this is group 18, because everything is very clean. But in the past, the periodic table has had different labels for the groups on top. So in the past, I will put this in red. Some books still use this, some literature still use this, but in general, we're going to use these numbers down here, but depending on what you're using, you may see something different. This column was called column 1A, and this column was called 1B, and then when you skip all the way over here, you have actually, sorry about that. I apologize for that. I'm on autopilot and made a mistake already. So this is 1A, and this column, when you look at another book, will be 2A, and then over here, this will be 3A, and then 4A, and then 5A, and then 6A, and then 7A, and this one over here was 8A. So first of all, you notice something different. There's this A business here. You'll understand why in just a second, but I just want to call to your attention that depending on what book you might be using or what periodic table you might be using, you might see different labels up there. It's just a label. Who cares if we call this group 2A or group 2? Who cares if we call this thing group 15 or group 5A or group 18 and group 8A? And you'll understand more about the numbers here later. It again has to do with electrons. It depends. It has to do with how many electrons fit in the orbitals around the atom, okay? But down here below, I'm not going to fill this entire table out, but this is 1, 2, and this is 3A. This one down here was 3B, and this one here was 4B, and this one here was 5B, and so these are the B's here. And again, the reason why there's a set of A elements and a set of B elements is because of how the electrons are. I told you just a second ago that the reason this table looks the way it is with these weird blocks here that are set down and this is spaced out, it all has to do with when we talk about electron configuration, how the electrons fill up. For the exact same reason, when they did the original labeling, they called some of these A group, or A groups, and that has to do again with electrons, and some were the B groups, and again that has to do with electrons. For our class, I don't want to get into the history of why it was done that way. I'm just letting you know that depending on the book you use, some people might refer to this as group 4, and some people might call it 4B. Some people might call the noble gases group 8A, and some people might call them group 18. And then we have the different labeling there as well. All right. We talked about copper, silver, and gold being the coinage group because we used it to make our coins. And then there's a couple of other things I want to talk about. Group 1A is this column, group 1 or group 1A, however you want to call it, or however we want to refer to it. These have a special name that you're going to see, which is called alkali metals. So if you're ever in a book or just reading a research paper and something talks about the alkali metals, you know it's got to be one of these here. And then we have group 2A, which is not alkali, it's called alkaline earth metals, right? So we have the alkali metals here, and we have the alkaline earth metals right next door. It's just something you might see referenced, that's all. And then over at 7A, we have the halogens. And over here at 8A, we have those noble gases. There are other names for other groups, but these are the most important ones. You have the alkali metals and the alkaline earth metals on the left side of the table, and then you have the halogens and the noble gases on the right side. So this group right here is called the halogens, and this group is called the noble gases, and this group is called the alkaline earth metals, and this one's called the alkali metals. All right, what else do I want to say? Metals are on the left. We lose electrons on the left of the table. Nonmetals are on the right. We gain metals over here. Metalloids are the elements that are near the stair-step line because they have properties of metals and nonmetals. So in general, as you start here and work your way to the right of the table, you get more and more non-metallic-like eventually until you reach the complete nonmetals. And what is the difference between a metal and a nonmetal anyway? In general, a metal is something relatively shiny, has some luster. It's pliable and ductile. You can usually draw it into a wire of some kind, right? It's usually a good conductor of electricity and a good conductor of heat. And these in general are the elements on the left-hand side of the periodic table, all right? You can see the copper, everything we make wires out of is on the left-hand side. These are metals. And of course, the ones in the middle, we call them transition metals because we're transitioning from the metal side to the non-metal side of the table. Now, in your mind, what is a nonmetal? A nonmetal is something that's not metallic in the sense that you can't draw it into a wire. It's brittle. If you try to pull on it, it's probably going to break. Think about charcoal, which is carbon. If you just think of carbon like a carbon briquette, you could break it. If you try to pull on it, it's going to break, right? They're not shiny or ductile. You can't pull them. And also gases are nonmetals. So you have a lot of gases over here like oxygen. Of course, it looks nothing like a metal. So as you move from left to right along the periodic table, you get from a metallic character gradually transforming to the non-metallic character on the right-hand side. And the last thing we'll say is that the groups up here that have the A's up here, these are called the main group elements. I guess I'll write that down. Main group elements. And just to help us remember, that's 1A through 8A. 1A to 8A, those groups. Now, why do we have a special label for the main group elements up over here, like these, and then these, and you exclude everything else? That is because those elements are what we're mostly going to be concerned with in a beginning chemistry class and even in organic chemistry. Again, the chemistry of life, the complexity we have around us really is only a handful of elements that participate in that. It's mostly carbon, nitrogen, oxygen. There's some other things that are involved as well, depending on what you're talking about. But generally, life is concerned with a handful of elements there, plus the hydrogen. And then you have other things like salt, sodium chloride, calcium for your bones, things like that. You know, these are in this column here. So this column is very important. And these columns, or groups I should say, are all very important. These are important as well, but you know, they're kind of secondary. They're important for other things. So we call these the main group elements because we really are going to focus on these mostly in this class. We will, of course, do problems and talk about what happens with these, but that mostly you study that stuff a little later in more detail. These main group elements are more important for us here in the beginning. The last thing I'm going to say before we actually solve our problem is that notice hydrogen is over here hanging out with the metals. These are all metals and hydrogen is over here. Obviously, hydrogen is not a metal. All right, but the reason it's over there is because hydrogen is a little bit of an oddball. It's the lightest and the simplest element we have. There's only one proton in the nucleus and one electron. It's just one proton, one electron, and that's it. And what happens is hydrogen can go both ways. Hydrogen can lose electrons, just like the metals do here, can lose electrons, or it can also gain electrons as well. So because it gains or loses electrons, you got to figure out where to put it because, you know, generally the metals like to lose the electrons and the nonmetals like to gain electrons, but hydrogen can do both depending on what's going on. So we just kind of put it over here in the metal column, even though it's not really a metal, but it can behave like a metal. So that's why it lives over there. All right, so now that we have that done, what we want to do is we want to solve a quick little problem, which is going to be very simple. And this problem is going to be that I'm going to write an element on the board, and then what we want to do is classify it as a metal, a non-metal, or a metalloid. All right, so the first one, chromium. So let's take a look at chromium. Right, so we want to write down the symbol for the element. We want to write down its atomic number, and we want to also classify it as a metal or a non-metal. So just getting practice with the periodic table. So chromium. So chromium's right here. It says chromium, and Cr is the symbol, and 24 is the atomic number. That means chromium has 24 protons in the nucleus, and for the neutral atom of chromium, it has also 24 electrons. There also are neutrons in the nucleus, but these numbers don't tell us how many are there. Different flavors of chromium, which we call isotopes, can have different numbers of neutrons that are there. But as far as the protons in the nucleus, it has 24, and 24 electrons to balance it out. So chromium, the symbol there is Cr, and there's 24 for the atomic number, and it's a metal. Forgot to mention that part. Why is it a metal? Chromium is a metal only because it's on the left-hand side of the periodic table to the left of the stair-step boundary. Okay? So I think what I'm going to do next is I'm going to write down the remaining ones here, and then we're just going to look them up. So next we're going to do helium, and then after that we'll do phosphorus, and after that we'll do zinc, and then after that we'll do magnesium, and then after that, we'll do bromine. And then after that, we'll do arsenic. Don't want to eat any arsenic. Not good for you. All right, so let's go take a look at helium. Is it a metal? Is it a non-metal? What's its atomic number? So here's hydrogen. All the way on the right-hand side of the periodic table is helium. It is a non-metal because it's on the right, and it has 2 protons because its atomic number is 2. The symbol is He. How many electrons does helium like to gain or lose? Well, actually, helium is a noble gas. It doesn't gain or lose any electrons. It's very non-reactive. So it just hangs out and it has its 2 electrons and it doesn't do anything. So that doesn't really like to gain or lose any electrons there. So helium, the symbol is He. The atomic number is 2, and it is a non-metal. Right? Next one, let's take a look at phosphorus. Phosphorus, right here, says phosphorus. Symbol is P. The atomic number is 15. And so that means 15 protons in the nucleus and 15 electrons surrounding the nucleus. And it's a non-metal because it's to the right-hand side of the periodic table. It's not really on the border here, so it's not a metalloid. It is a non-metal. So symbol is P, and there are 15 protons in the nucleus, atomic number 15, and it's a non-metal. Okay, next. Let's talk about zinc. Where does zinc live on this periodic table? We look over here for zinc. Here it is. Zinc, atomic number 30, and the symbol is Zn. And it is a metal because it's to the left-hand side. Now, we know that zinc likes to lose electrons because in general, all these metals like to lose electrons. But exactly how many electrons zinc loses, you can't really say so much from the periodic table. The ones on the edge are very easy to predict. They're very reproducible. But zinc, you have to maybe look it up in a table. You'll probably memorize it after a while of dealing with zinc, but I'm just saying that you can't just count based on the periodic table for the elements in the center there. So atomic number 30, Zn is the symbol. All right, so Zn, atomic number 30, and that was a metal. And so because of that, it likes to lose electrons. All right, what about magnesium? Magnesium. Magnesium is right here. Here's magnesium. Mg is the symbol. Atomic number is 12. Now, bonus question. How many protons does it have? 12. How many electrons does it have? 12 electrons. And does it like to gain or lose electrons in chemical reactions? It likes to lose electrons. It wants to lose, if it loses 1 electron, then it would have an electron configuration similar to sodium. If it loses 2 electrons, it'll look more like neon. So it always likes to lose 2 electrons. So what we could say is magnesium, the symbol is Mg, and the atomic number is 12, and it's a metal. And it's a metal because it's on the left-hand side of the periodic table. What about the element bromine? What about the element bromine? So bromine is right here, and its symbol is Br. Its atomic number is 35, so 35 protons, 35 electrons, and it would like to gain 1 electron to be as close as it can be to the electron configuration of krypton, which is right next door. So it likes to gain an electron there. So Br is the symbol, 35 is the atomic number. So Br is the symbol, and 35 is the atomic number. Is it metal or non-metal? Everything on the right is non-metal. So that's what that is. And the last one here is arsenic. Don't want to eat any arsenic. It's poison. So where is arsenic? Arsenic's right here. The symbol is As. The atomic number is 33, so 33 protons, 33 electrons. And is it a metal or a non-metal? Well, it's actually right on the border of this line here, so it's neither metal nor non-metal. It's what we call metalloid. Okay, metalloid. So atomic symbol is As, 33 for the atomic number, metalloid. All right. So, in truth, this is the lesson that when I started chemistry, I wish somebody had for me, right? Because these things that I'm telling you, these are, I mean, there's always in every textbook, in every lecture that you have by a professor or whatever, or a teacher, you always have an overview of a periodic table. But these are the things that I think are the most important things about the periodic table. I could have broken this into probably 2 or 3 lessons and made it shorter, but then you would lose the continuity of what I'm trying to say. The most important things for you to understand about this table is that it has the funky shape that it has because of the way electrons fill around these atoms. And we haven't learned that yet, so I can't really teach it to you. But trust me, later on when I teach you how the electrons work and how they fill up, you'll understand exactly why it looks the way it does. But we got to get there, right? Secondly, it's called the periodic table because as you increase the number of protons in the atoms, you see regular periodic patterns. You see these special gases which are regularly spaced, which we now call noble gases that don't react with anything. And now we know that they're that way because they don't have, or because they have a very stable electron configuration. They don't like to gain or lose electrons. When I say stable, I mean the nucleus can hold it very tightly. I mean the nucleus of those guys, the way the electrons are distributed, the nucleus is able to hold them all very tightly. And because the electric force is so incredibly strong, millions of times stronger than gravity, we've said that a million times, because of that, it can hold these electrons very tightly and not let them go. That's basically the bottom line. And I'm going to teach you why that's the case later. Now, the elements next to the noble gases on either side are very reactive because they're always trying to get an electron structure as close as possible to the noble gases. Why? Because the noble gases are really stable and the force, the electric force, can hold everything in place. So everything to the left is trying to gain a single electron to be close to these. Every thing 2 spaces over is trying to gain 2 electrons to be close to its noble gas. Over here, this group is trying to lose an electron to become like its nearest noble gas. It's trying to lose an electron to be like its nearest noble gas. And the same thing, this one's trying to lose to be like its nearest noble gas. And then the one here is trying to lose 2 electrons and lose 2 electrons. So there's a symmetry, right? The ones near the right-hand side are trying to gain 1 or 2 electrons. The ones on the other side of the table are trying to lose 1 or 2 electrons. And this is the pattern that we laid out in the beginning of the lesson that I was telling you, the periodic nature. We said this table has rows, which we call periods, and it has columns, which we call groups. And we said that the names of the groups have basically changed over the years. In older books, you see these main group elements, which are all of these and all of these, labeled 1A, 2A, and then all the way through 8A. The reason there's 8 is because of electrons. We'll talk about later why, but they're very important, and that's why. But that's why they're this way. We call these the transition metals, and they have B's associated with them, again, to differentiate the difference in the way the electrons are laid out between this group of elements and then these right here. All right? And then we basically said that this table is constructed always, on every book you'll ever see, it's got the book here, the table listed as we have here, with 2 extra rows down here. One row called period called the lanthanides, and the other one called the actinides. And the way it's supposed to be drawn is to show you that this kind of fits in there and kind of spreads the table apart. So if you really drew the actual table, it would actually look like this with the table spread far apart. This is going to help us a lot when we study electrons to know what these different things, what these different areas of the table are. But you just don't usually see it like this because you can't print it on a page very easily. All right. Then we said that we had some special names for some of these different groups. We had the alkali metals, we had the alkaline earth metals, and then we had the halogens, this one here, and then we had the noble gases. And then we talked about metals and nonmetals on the left and on the right, metalloids right here near the stair-step line, transition metals throughout here, and that's basically it. Then we did some practice. So I just wanted to go through it again because it is a lot of information. And I could have written all this stuff down, but at the end of the day, it's going to be faster if you just watch this lesson a few times, to get the lay of the land. I promise you what we'll do. In the next lesson, we'll solve a few more problems here. And then as we really study chemistry and use what's on this table, because of this introductory lesson, you already know now what this table is used for. I have not hidden anything from you. A lot of books and teachers will kind of hide what the table is for until later. I've given it to you. So now when we go in the next few lessons and write down what a chemical compound looks like, you're going to know, we're going to review it again, but you basically know how the electrons are doing their thing, and we're going to apply that in future lessons. And it might take a few times for you to for it to sink in. That's okay. It took hundreds of years to discover this stuff. So if it takes you a few viewings of a video, please cut yourself some slack. Nobody learns this stuff overnight. I'd like you to watch this a few times. When you feel like you understand what's going on, follow me on to part 2. We'll do a couple more problems, just getting practice with using the periodic table.
Learn anything at mathandscience.com.